Let's talk about limiting reactants. What is the limiting reactant anyway? So reactants are the guys who are going to react, obviously, and when we have a limiting reactant, the way we know that we have that kind of problem to begin with is that we have amounts of more than one substance that we start with. So let's start with 40 grams of ammonia, and we're going to start with 80 grams of copper 2 oxide. And what we're going to do is react these guys together. And here's the balanced equation. We've got 2 ammonias and 3 copper 2 oxides, and this will produce 1 molecule of nitrogen, 3 atoms of copper, and 3 molecules of water. This is a way to get elemental copper from copper oxide. So if I have this problem, and I'm looking at it and I'm saying, is this a limiting reactant problem? I look at this and say, ammonia is a reactant, and I have an amount of that. Copper 2 oxide is a reactant, and I'm given an amount of that. I don't know which one is going to limit how much I can make. Or I'm going to run out of one of these guys before the other, presumably. And my job is to say, which one did I run out of first? That will limit how much of the product I can make. So what we're going to do is we're going to figure out from each of these how many grams of copper I can produce. And that's going to give us a clue. There are a couple different ways to do limiting reactant problems, but this is one way that works really well. So 40 grams of ammonia is one of the things I'm starting with. And all I'm going to do is 2 different calculations in parallel here. I'm going to start with my 40 grams of ammonia. I'm also going to start with 80 grams of copper 2 oxide, and I'm just going to compare them. And remember that when we're doing these stoichiometry things, we're going to start with, if we're starting with grams of something and going to grams of something, I'm taking grams of A, going to moles of that same A, whatever it is, changing that to moles of B using the coefficients of the balanced equation, and then going to grams of B. So this is my basic plan, and I'm going to follow this plan for both of my reactants. So I know that there are 17.03 grams of ammonia in 1 mole of ammonia. So that's great. I've now translated into moles so that I can talk to the balanced equation, and the balanced equation tells me that 2 moles of ammonia as a starting material will produce 3 moles of copper. And I also know that 1 mole of copper is 63.55 grams. I need to get back into grams, into the macroscopic world, so that we can actually measure something on the balance. As I do this, I can look at this and say, oh, I need 3 sig figs, so my answer will be 224 grams of copper. Okay, if I have enough copper 2 oxide to use up all of my ammonia, I would get 224 grams of copper. We don't know if we've got enough copper oxide for that, so let's go figure that out. I can look at the periodic table, add up the molar masses, and come up with 79.55 grams of, grams, put grams in there, grams of copper oxide is 1 mole. So now I've translated into mole language so that I can look at the balanced equation, and it tells me that if I have 3 moles of copper 2 oxide, I will get 3 moles of copper out. It's a 1-to-1 ratio. It's important to put that in there, though, because that ratio is not the same as the one for the other reactant. So we have to be sure that we always look at our ratios. And again, we have the same molar mass, of course, for copper. And I'm going to use 3 sig figs again and come up with 63.9 grams of copper. What this tells me is that if I am able to react every bit of my copper to oxide, and I have plenty of ammonia to do that, that I would get 63.9 grams of copper. Now look at these 2 answers. They are not the same. They're wildly different. So this is the tricky part for some people. So let's think about this a little. What this first number tells me, the 224 grams of copper, is that if I have plenty of copper 2 oxide, that I can use up every bit of my ammonia, I would get 224 grams. If I'm limited by the ammonia and not by the copper 2 oxide, that is what I'll get. The other number tells me if I'm limited by my copper 2 oxide and I have plenty of ammonia, then I will get 63.9. Limited, let's put here, limited by copper 2 oxide, excess ammonia. And this one tells me that I'm limited by the ammonia, but I had excess copper 2 oxide. So if we look at these two numbers, which one's smaller, which one's bigger? 63.9 grams of copper is how much I make. At that point, I've run out of copper 2 oxide. So the smaller number is going to be the actual answer. This is the actual answer. My theoretical yield is the smaller number. The bigger number is not possible, because by the time I hit 63.9 grams of copper, I have run out of copper oxide. I don't have enough to keep going and using up all of the ammonia. I don't get to use up all the ammonia. The ammonia is excess. I have more than I need. So my theoretical yield is 63.9 grams of copper. That's great. Then the other piece of information I'm getting out of this is that copper 2 oxide is limiting. In this case, it's our limiting reactant, and ammonia is in excess. We can't make 224 grams of copper because we've run out of copper 2 oxide long before. Notice that we had more by mass of copper 2 oxide than we did. We had twice as much. We had 80 grams. We only had 40 grams of the ammonia. So you cannot tell by the starting amounts just looking at it. You cannot predict just looking at it which one is limiting based on amounts. You have to do the math. You have to plug in the molar masses and the ratios, the coefficients from the balanced equation, and you have to chug it through. Another way, an alternate way, in case you're wondering about this, is to just determine which one's limiting if you don't need to predict the amount of product, is to just take ammonia and convert it to copper 2 oxide. Take one reactant, convert it to the other one, and see how that compares to how much you actually have. And that will get you the answer for the limiting reactant in just one calculation, but it won't tell you how much you could make of the product.